This is Algebra 2, Unit 10, Lesson 6, and this lesson is on common logs. Common logs we have talked about before, but we didn't call them common logs. Remember when we referred to anything with a log base 10, we said that it could just be said to be, like if we have log base 10 of 2, that's the same thing as log of 2. Anything that does not have a base number in it, any log that does not have a base number in it, is understood to be a log base 10. And log base 10 is referred to as the common log. So anytime you have a log base 10, that is also known as the common log. Now, we've also said that we could solve a problem like this by converting these to both the same base. So this is 8 to the x. 64 is the same thing as 8 squared. So we can solve that by saying x equals 2. As long as we can get the bases the same, we can solve any equation that I give you. But what if we have something like this, where we don't have bases that are the same? With that, there is no way I can solve that unless I use logs. And this is what I meant when I said earlier in the chapter that logs are going to open up all sorts of problems that we haven't been able to solve yet. Because with this, if we convert that to a common log, we're going to be able to solve it very easily. With this, we could convert that to log base 3 of 11 equals x. But still, the only way the calculator will do this problem is if we can do base 10, because calculators only do log base 10. So there has to be another way to solve this problem, and to do that you're going to convert it to a common log problem and use the properties. So let me show you how to do that. So I've rewritten that problem here. We've discussed that there's no way to solve this because the calculator won't do this unless we convert it to a log base 10, and we don't know how to do that. So I'm going to show you how to solve this using common logs. And what I would do is anytime I have something like this where I cannot get the bases the same and I can't solve it. Now, if you could get the bases the same, I personally think that's usually the easiest way to do it. Just get the bases the same and then set the exponents equal to each other. But if that can't be done, you have to have a way to solve this problem. And to do that, what I'm going to do is I'm just going to put a log in front of both sides of this equation. Remember, when you're solving equations, as long as you do the same thing on both sides, you're allowed to do that. So I'm going to place a log in front of the 3 to the x, and I'm going to place a log in front of the 11. Now, by placing a log in front, it is understood that this is a log base 10. Okay? Now, honestly, I could put any log in front. I could do log base 2, log base 5, log base 8, but then I won't be able to put it in my calculator to get an answer. So the only kind of log I can get an answer with in my calculator is log base 10. So that's what I want to convert everything to, a log base 10. I'm going to use my properties to solve this so that I can get x by itself. So if I move the x to the front, x log of 3 equals log 11. Then I'm going to divide both sides by the log 3. So x equals log 11 over log 3. Okay, so this is going to be my answer. If it asks you to get that as a decimal, and most of the time they will, what you'll do now is you'll just put in your calculator or in Desmos log 11 divided by log 3, and you'll get a decimal for that. I end up with a 2.183. I'm going to round that to 3 decimal places. You'll just have to pay attention to the homework assignment and round to the number of decimal places that they ask you to round that to. Okay, now, I want to compare what I've got right here with what we said over here. Now, we said that we could convert exponential functions to logarithmic functions by making the base number here a base of the log, and the number here is our x value, and the exponent is what it's equal to. Now look at what I've got here. If you compare this to what I've got over here, well, x and x, they're equal, right? If the x's are equal, well then can I assume that the log base 3 of x is equal to the log 11 over log 3? Okay? So log base 3 of 11 is the same thing as log 11 over log 3. Because they both equal x, they have to be equal to each other. Okay, so if you look at this, this is something called the change of base formula. And this is going to help you with some logs that we haven't been able, well, we've been able to solve them, but it took a lot of work to solve them. With this change of base function, if you have a log base something of another number and your log base is something other than 10, now log base 10 you can just plug in the calculator, there's no need to do this. We can convert any log of any base to a log base 10 if we know the change of base formula. And all you have to do here is, whatever this part is, it would go on top attached to a log 10. And whatever the base is, it would go on the bottom attached to a log base 10. So log 11 goes on top, over log 3 goes on bottom. Now I could put that in my calculator and solve it and know that that's equal to 2.183. So that change of base formula is very simple. It makes sense mathematically with all this that we did, and we can use the transitive property to see that these two things are actually equal. So no matter what log base I give you, you can convert it to log base 10 and solve it in your calculator very easily. So here are a few more problems. There is no way to get the bases the same for any of these. So I'm going to put a log in front of each side and solve it from there. So for this one, I would have log of 5 to the x equals log 62. I'm going to use my properties. X log 5 equals log 62. So x equals log 62 over log 5. And when I put that in my calculator, I get 2.564. Also, you can put it into Desmos as well, either one. For this one, there's no way to get the bases the same, so I'm going to put a log in front. Log of 5 to the 3y equals log of x to the y minus 1. I'm going to use my properties. 3y log 5 equals y minus 1 log 8. My goal here is to get y by itself so that I can solve it using the calculator. So if I do that, I'm going to want to distribute here. So I've got 3y log 5 equals y log 8 minus log 8. If I get all my y's on the same side, I would have a 3y log 5 minus y log 8 equals negative log 8. Then I'm going to distribute out the y. So I've got 3 log 5 minus log 8 equals negative log 8. And I can divide by everything that is not y. So y equals negative log 8 over 3 log 5 minus log 8. I would then go to Desmos and plug this into Desmos to get my answer. When you plug something like this into Desmos, you do need to make sure you put parentheses around the top and parentheses around the bottom so that you can get the correct answer. So when I do that, that gives me a negative 0.756. Then for that last one, I'm again going to put logs in front. So on the left-hand side, I would have log 4 to the 2x equals log 9 to the x minus 1. I'm going to move the exponents to the front using my properties. 2x log 4 equals x minus 1 log 9. I'm going to distribute here. This side stays the same. 2x log 4 equals x log 9 minus log 9. I will get the x's to the same side. 2x log 4 minus x log 9 equals negative log 9. I'm going to distribute out the x. So I've got 2 log 4 minus log 9 equals negative log 9. Then I divide by everything that is not x. So I've got x equals negative log 9 divided by 2 log 4 minus log 9. So this seems a bit complicated, but when you're dealing with these equations, the rules for equations that you learned in Algebra 1 still apply to all of this. Just because the numbers look a little messy and they've got some logs in them, those basic principles still remain the same. You can still use all those methods to solve these equations. And then once you get to the end, you plug it in Desmos and you're done. So it's pretty simple once you get the math down. And again, it's just solving a basic equation. It's just got some more complicated numbers in it. So when I plug that in Desmos, I end up with a negative 3.819. Again, I'm rounding to 3 decimal places. So for these two examples, with this one, I could convert it to exponential form if I want and then put a log in front of each side. But if I recognize that I could use the change of base formula here. If I have log base something of something equals a variable, that automatically, when I see something like that, I know to do the change of base formula. It's going to save me work. If I convert it to exponential form and then put a log in front, I'm going to have a lot more work than if I just say, well, I recognize that that is the same thing as log 12 over log 5 for the reason that we had in the beginning of this lesson. So log 12 over log 5 equals x. So I'm going to convert that to a decimal right away using Desmos. So if I put in Desmos log 12 over log 5, I end up getting 1.544. For this one, I recognize that that's the same thing as log 25 over log 4. And I can plug it into Desmos right away. When I plug that into Desmos, I get 2.322. So now it's time for you to practice. Go ahead and pause the video, write these two problems down, solve them on your own, try to use as few steps as possible, and we'll come back and compare answers. And for your answers here, we've got, I put a log in front here, so log 3 to the 3x. If I use my properties, I have 3x log 3. Over here, I have log 4 to the x minus 1. If I use my properties, I have x minus 1 times log 4. I distribute it here, giving me x log 4 minus log 4. I move the x log 4 to the other side. So I have 3x log 3 minus x log 4 equals negative log 4. I'm going to distribute out the x, leaving me with 3 log 3 minus log 4, which is what I divide on this side. And that gives me an answer as negative 0.726 when I plug that into Desmos. On the other one, hopefully you recognized that this is the change of base formula. So that's log 7 over log 8, giving me a 0.936.